Today we're going to talk about combinations of functions. This is section 1.6 in your college algebra book, and combinations of functions is pretty much what it says. You're combining the functions, and there's two main ways that we do that. One way is going to be the kind of the obvious addition, subtraction, multiplication, division, kind of taking two functions and combining that way. Another way is to do composite functions, if you'll remember doing like f of g of x or g of f of x and that kind of thing. All right, so not only are we going to talk about how to combine them, we're also going to talk about their domains, and that's kind of the tricky part that you need to pay close attention to. Okay, so let's start off with the operations version. Okay, so we're going to look at combining functions with addition, subtraction, multiplication, or division. Okay, so this is the notation. This is how we write that we're going to add two functions together. So notice you do your f plus g here. I wanted to point this out because this is the tricky one. If you just see fg together, that means multiplication. Sometimes that gets confused with f of g of x, but that'll look different. So fg is multiplication. So let's try fg of x. So that means I'm going to take these two functions right here and I'm going to multiply them together. So what I'd end up with, fg of x, is just taking 1 over x times x over x minus 1. And I'm going to multiply straight across. However, I can reduce, just like with numbers, if you have something on the top that can reduce with something on the bottom, you can do that. So these two x's are actually going to cancel out, and I end up with a 1 over x minus 1. Okay, so that's all you're doing, just combining that way. Now let's look at finding the domain of that problem. So I just did it. Let me rewrite it here, what my final answer was when I did that. I got fg of x to be 1 over x minus 1. Okay, so when you do the domains on two functions that you have combined together like this, you actually have to do more than just look at your final result. Because you were using these two functions within that problem, you have to look at all three functions involved. Okay, so that's important. You look at all of the functions involved. So that means I have to look at the domain of f. So come up here and look at f. Well, it's a fraction. I don't want my denominator to be 0. So that's why x can't be 0. I also have to look at the domain on g. So I come over here and say, oh, it's another fraction. I can't let my denominator be 0. So that means x can't be 1. And then I also have to look at my final result after I multiplied them together, and that's up here. And again, I wouldn't want x to be 1. I have to look at all three of those domains and combine any restrictions at all that they have. So it looks like overall, for my final domain, x can't be 0 or 1. But you have to look at all three. You can't only look at the result. I wouldn't have noticed that x can't be 0, but it would have created a problem early on in that problem. So there you go. So let's practice a little bit. I've got three different functions up here that we could use. Let's go ahead and begin by finding the domain on each one of them. So in this first one, remember that you do not want your radicand to end up negative, because that's going to give you an imaginary number. So that means x minus 2 has to be greater than, I'm going to sneak that up here, x minus 2 has to be greater than or equal to 0. So x has to be greater than or equal to 2. I'm going to write that in interval notation. So it's got to be anything from 2 to infinity. Okay, this next one is not a fraction. It is not a radical, so I have no problems with x being anything at all here. Same deal with h of x. No fraction, no radical, just negative infinity to infinity. Okay, so now we're going to do two things. We're going to find the combined function, and then we're going to come back and look at what its domain would be. So I'm going to take the f function, which is the square root of x minus 2, and I'm going to divide it by the g function, which is 3x squared. Now sometimes there's simplifying that can be done, but in this problem, with that radical there's nothing I can really do. I'm just pretty much writing it down, whatever operation they want me to do. The bigger question here is to practice that domain. So you have to look at what all is involved. So we have to do the domain for f, for g, and for f divided by g. All three of those. So when you look at f, we had a domain of 2 to infinity. G didn't have any restrictions whatsoever. And if you look at your final result, well now, all of a sudden I have a couple issues. I have a radical, and I want to make sure that that stays positive. So that means that I've got to make sure that it falls within this range, which is what I had written earlier for f. But I also have now created a fraction. And by creating a fraction, I have to be wary of making this denominator be 0. So I can look at that and say, well, I wouldn't want x to be 0, because that's how that's going to happen. So then not only do I have to go from 2 to infinity, but x also cannot be 0. And then I have to combine all of that stuff together to come up with my domain. So the g does not create any issues for me. The f does, but it's already incorporated down here. And so it looks like this right here would be my overall domain. But let's think about this for a second. If I'm going to make the value of x be somewhere bigger than 2, is this really even going to be an issue then? Because I think this makes sure that it's not 0, because I'm making it bigger than 2. So I don't really need to write this. My overall domain will be 2 to infinity. And this is kind of how I want you to write this, where I know I can see that you have acknowledged that you have to check all of these different domains, because I'm going to mix it up on you in a little bit. So you have to recognize combined functions. You have to do all three. All right, let's try one more. I've got those same functions up there, so you can look back at your notes at your domains. This time I'm going to do g minus h of x. So that means take the g function, 3x squared, and I have to subtract the h function. Okay, on this one, I need to kind of remind you about you're subtracting the whole function, so let's put it in parentheses, and you're going to end up having to take that minus sign and distribute it. So it's going to end up 3x squared minus 2x squared minus 4, which then would simplify to x squared minus 4. So that's your final answer. That's what it simplifies to. Okay, when you're doing your domains, you have to do the domain of all three. And if you look at this, and you have to look back at your notes on this, remember we have to look at g of x. We had said it was negative infinity to infinity. We have to look at h of x. It was negative infinity to infinity. And if you look at your result, it's also not a fraction or a radical, so it's going to be negative infinity to infinity. So your overall domain, even after looking at all three of those functions, still ends up being negative infinity to infinity. Which many, many times that is what your domain is. There's so many functions that have no restrictions whatsoever. Okay, last thing. What I'm going to do on this one is g minus h of negative 3. So all that means is, hey, take your g minus h function and plug in negative 3. Okay, so right here is my g minus h of x, and I'm going to plug in negative 3. So if I plug in negative 3, it's going to be a negative 3 squared minus 4, so 9 minus 4 gets me a 5. And so that's how we would evaluate it at a certain point. I want you to notice, though, that this works more than one way. That was easy to plug in because I had really already done all the algebraic work over here. But if I hadn't done this problem and it just asked for this, well, I could still do what I did. And on your assignment, I'll have you kind of show it both ways, but you do it not every time, but it's just for you to recognize there's two ways to do this. I could also just do g of 3 and subtract h of 3. Let's look at what would happen if we did that. So if I plug 3 into the g function, that would be 9 times, I'm sorry, not 3, negative 3. We're plugging negative 3 in for both of those. Okay, so plug in negative 3 and square it. That would be 9 times 3. Well, that's a 27. On h of x, when I plug in negative 3, I'm going to square it, so now it's 9. Times 2 is 18. Plus 4 is 22. So I end up with 27 minus 22. That's 5 also. Either way works. Use whichever way you like best. Okay, let's move on. Now, instead of combining functions with addition, subtraction, multiplication, division, the second type that we're going to have are composition functions. Okay, so a composition function is one, and there's different notation. This is probably the notation you're most familiar with, f of g of x, which really just means you're going to take the g function right here, and you're going to plug it into the f function. Okay, this first one is another notation that's really more common in upper level math books. It's just still said f of g of x, and you're going to take your g function and plug it into your f function. I tend to use this method here more as far as when I'm writing it, but you have to be familiar with both of them. They both pop up. All right, so let's try it. In this problem, they want us to find h of g of x. So that means I'm going to take my g function, plug it into h. And then I'm also going to work on the domain. Okay, so let's take the g function and plug it in for x in the h function. And it basically just becomes 1 over x minus 2. Now you're not multiplying it, it replaces the x that's there. So notice this x totally disappears and it gets replaced. Okay, now when you're working on domain, it's a little bit different than when we were doing our combination. In this problem, remember, I'm just rewriting my answer from that previous slide. When you're doing your domain, it is the combination of the domains of the first function used and the resulting composite function. That's only 2 domains we're checking. It's not 3. Here's the deal. When I do this right here, I take the g function and I grab it. So I have to make sure that I use something that's good on the g function. That's my first one. So that's the first function used. But I immediately go plug it in to the other function, which changes this function entirely. So I never really used h of x by itself. So I don't care what the domain on h of x is. But once I've plugged that in, I have to then look at my result. So there's only 2 domains I'm looking at. I look at the domain of the original, and this one is not a fraction or a radical, so it's all reals. And then I look at my end result, which is up here. My end result, I would not want x to be 2. Notice I never ever used the h of x domain, because that would have been a problem for a 0. But it works out fine. I don't care about 0 being an issue here because I never used h of x by itself. Okay, so overall, x can't be 2. All right, so the big thing is that you recognize on these problems, you're only checking 2 domains. The other problems, you're checking all 3. So let's practice this. First thing I'm going to do is go ahead and get all of my domains written. So let's come up here. This f of x is not a fraction or a radical, so negative infinity to infinity. G of x, not a fraction or a radical. However, h of x is a fraction. I would want to make sure x does not equal 0. All right, so first we're going to go ahead and do the operation. So I'm going to take the f and plug it into the h function. So it's going to become 1 over, and instead of writing the x, I'm taking this f function and I'm putting it in for x right here. So now my new denominator becomes 3x squared minus x. And I'm done. I mean, that part of it is the easy part. The domains, we've got to check. So we have to start by checking the domain of the original function. The original function was f of x. That's what I grabbed and went and plugged in. So I'm going to check F. That doesn't have any restrictions at all. And then I bypass the other function and I go straight to my result. So my result is the h of f of x. And that domain I haven't found yet, but I'm going to. I cannot let that denominator equal 0. This is a little trickier one that maybe we haven't done where you have to work a little bit to figure out what is going to make that be 0. And in fact, remember, we don't really want it to be 0. But you can still treat it like you're doing an equation. All right, so this is a quadratic, so I'm going to need a factor, and I'm going to pull out a GCF. Pull out the x, I get 3x minus 1. Set them each not equal to 0. So 3x minus 1 does not equal 0. So then x could not be, add the 1, divide by the 3. Okay, so here are my restrictions then. Okay, so let's come over here and write this. X cannot be 0 or 0 or 1/3. Okay, so then my overall domain, F didn't create any issues, but h of f of x did. So x cannot be 0, and it cannot be 1/3. One more example. Okay, so wanted to try this new notation for us. F of g of x. We take the g, plug it into the f. Okay, notice that I have the same three functions, so we've already found the domains for them on that previous slide. We can refer back to those. So let's take that g and put it in for x in the f function. Oops, sorry, I'm just going to circle that because that actually goes right there. It also goes right there. All right, so when I write this, it is going to equal 3. And instead of x, I'm going to put in x minus 2 squared minus, and instead of x, I'm going to put in x minus 2. All right, so there's some algebra here we have to be really careful of. First thing I'm going to do is square this quantity. Now, you can write that out twice, x minus 2, and do FOIL. Or you can use the shortcut, but what you can't do is try to just distribute the squared. That doesn't work. Remember, I'm going to do the shortcut. You square the first term, multiply the two terms together, and then double it, so that's going to be a minus 4x, and then square the negative 2. And then I'm going to have to subtract x and distribute this minus, so then it's a plus 2. Last step, let's distribute that 3. It's really not going to be my last step because I think I'm going to have some like terms. All right, so then I end up with final answer 3x squared minus 13x plus 14. Okay, so that's what the composite function gets me, but I still have to find its domain. I didn't leave myself very much room. I should have written a little smaller. I'm going to, what am I going to do? I'm just going to work with it. Okay, so since it's a composite function, you have to check two domains. You have to check the original function that you grabbed and went and plugged in. So my original function that I grabbed was not a fraction. Not a fraction or a radical, so it had no restrictions. And then I have to look at my result. My result down here, also not a fraction, not a radical. It's going to have no restrictions. So if I have no restrictions on either one of those, my overall domain will also not have any restrictions. So that one was easy enough. I could just squeeze that in there. It didn't have much going on. Okay, so let's do that last thing like we did before. What if you're throwing a number in there instead of x? So it's f of g of negative 3. So what I would probably do, since I've already found f of g of x, if I want to do f of g of negative 3, that means take negative 3 and go plug it in for x. So then I would end up with 3, put in the negative 3, squared, minus 13, put in the negative 3, add the 14. So that's 9 times 3. This is going to become plus 39 plus 14. That ends up equaling 80, I think. Okay. All right, and there's my answer. Let me go ahead and also show you an alternate way to do that. That worked out fine because I had already done all this algebra to get to this point, but that took me a lot of algebra. So I'm kind of thinking, well, gosh, if they only ask for this, and I had not previously done this, that's a lot of work to get to there. Is there another way? Well, yeah, there is. What you can do is you can find g of negative 3, and whatever you get for g of negative 3, go plug it in for f. So let's do that. Let's find g of negative 3. That means I'm going to put a negative 3 in for x into the g function, so negative 3 minus 2. So that gets me a negative 5. If that equals negative 5, then I'm going to take that answer, whatever I get for that, and I'm going to plug that in for f. So I'm going to take negative 5 and plug it in for f. So basically I'm finding f of negative 5. So that means, I'm going to come down below here, it's going to be a 3 times a negative 5 squared minus negative 5. Okay, so that becomes 3 times 25. This goes change, so it's a plus 5. Oh, look, there's my 80 again. And I didn't have to do all the previous algebra over here. Not that that's bad, you can do that, but either way will get you to the same answer. Okay, so I want to summarize that real quickly and make sure that you understand the difference between those things that we did. The first thing is, if you have what we call a combined function, that's adding, subtracting, multiplying, dividing. Then when you're doing your domain, it is the domain of all three functions involved. So it'd be the f, it'd be the g, and it would be the f plus g, or whatever operation you're doing. You have to look at all three of those. If you are doing a composite function, a composite function is like f of g of x, where you're taking one and plugging it into the other. I do not have to check all three domains. All I'm going to look at is the original function that I grabbed first, in this case g of x, and I have to look at the result, f of g of x. I never look at f by itself. And that's how you come up with your domain for those. Okay, you got to keep that straight when you do which. Okay, last problem. Okay, I like these. They're graphical combined functions. And so you're having to look at ordered pairs that are plotted and see how they can combine, because it works the same way as working with an equation. So if you look at this first example, we're doing f minus g of 3. Okay, so remember that we said that that's actually the same as finding f of 3 and subtracting g of 3. Well, let's do that. What is f of 3? So if I look in my f function and I plug 3 in for x, I'm looking at what's the y that I get back. Well, it's this ordered pair. If x is 3, y is 2. So f of 3 is 2. And then we'd go over to the g function and do the same thing. When x is 3, y is 1. So g of 3 is 1. And 2 minus 1 is 1. All right, let's try another one. This one is a composite function. I have to find f of g of 4. So I'm going to begin by finding g of 4. So go to your g function, plug 4 in for x, and tell me what you get back for y. Should be 0. So this is just 0. So now I'm going to do f of 0. So going to my f function, and if x is 0, what's the y value that goes with it? 4. So f of 0 is Okay, let's try this next one. It says f of 2, or it's g of f of 2, but I'm going to start by finding f of 2. So f function, x is 2, y would be 0. So now you're going to do g of 0. So going over here, in the g function, x is 0. The y that goes with it would be 4. Okay, then I have one more I want you to try on your own, a little bit quirky, f of 1. See if you can figure that one out. All right, you're going to plug 1 into the f function. So when x is 1, y is 2. And then you got to come back and find f of 2. So I'm using the same function. When f is 2, y is 0. There you go. Kind of fun. All right. Good luck with this.